Okay, 9.3, polar and rectangular forms of equations. So in this section, we're going to look at going back and forth between the two forms from polar coordinates to rectangular coordinates. So as we get started, remember, think back to chapters 4 and 5 maybe, where we talked about points on the unit circle and we related them to our trig functions. So remember that points on the unit circle can be written in terms of theta as cosine of theta, sine theta. Because remember that we related cosine of theta to the x value and sine theta to the y value. And when we had a radius of 1, it was just cos theta, sine theta. And that's how we could graph and plot points on our unit circle. Now, as we got further into the chapter, points on a circle with a radius other than 1, we could then write as r cos theta. And hopefully you remember that. And r sine theta. Okay, so keeping that in mind, we're going to use those things to help us with today's lesson. So if we let the polar axis and the pole in the polar coordinate system coincide what we know as the positive x-axis and the origin, we now have a way to convert polar coordinates, r theta, to rectangular coordinates, x, y. So, and it's as simple as looking above in what we just discovered or just discussed as old material. X was r cos theta and y was r sine theta. So making it official, looking here in this gray box, converting polar to rectangular coordinates, if a point P has the polar coordinates r theta, then the rectangular coordinates x, y of P are given by this right here. Again, x is r cos theta and y is r sine theta. And if you're kind of fuzzy on that, take a look at that diagram, which we've looked at many, many times. If we look at theta, we could say the cosine of theta is equal to adjacent over hypotenuse, so that's x over r. And if we solve for x, that is r cos theta. Likewise, if we have the y value, we could say that the sine of theta is equal to the opposite over the hypotenuse, y over r. So if we solve for y, we could say r sine theta is equal to y. So this is simply how we are going to convert. So xy is equal to r cos theta, r sine theta. So let's put this into practice. Find the rectangular coordinates, so we're going after xy, for each point with the given polar coordinates. So if we first look at point P, we have 4 pi over 6. So 4 is my r value, pi over 6 is my theta value. So I want xy for my final answer. So I know that x is equal to r cos theta. So if I plug in my values, that's 4 times the cosine of pi over 6, or 30 degrees. So that is 4 times the cosine of pi over 6 is root 3 over 2. So that is going to be, if I reduce, 2 root 3. So I have half my answer, 2 root 3. And now to get the y value, we're going to take y equaling r sine of theta and plug in 4 times the sine of pi over 6, or 30 degrees. I know the sine of 30 degrees, or pi over 6, is 1/2, so half of 4 is 2. So my final answer is 2 root 3, 2. These are my xy values. So 4 pi over 6 in polar coordinates converts to 2 root 3 over 2. And if you think about the location, if I'm in polar coordinates and I go pi over 6, then I am in the first quadrant and I would go out 4. Maybe I'm somewhere here. Well, if I overlay the xy axis, 2 root 3 over 2, I'm in the same approximate location. So we kind of can have some confidence that we did that one right. Now, because it's pi over 6, it has a nice, that's a nice reference angle. Always make sure that you use the exact values, no decimals on that. I know you might be tempted to go to your calculators, but we definitely want to stay with exact values when we can. Okay, let's look at B. So Q is negative 2, 135. So X is equal to R cos theta. So that's going to be negative 2 times the cosine of 135 degrees. Well, 135 degrees is in the second quadrant. Cosine will be negative. The reference angle is 45, and the cosine of 45 is root 2 over 2. So that's negative root 2 over 2. Two negatives make a positive, and those 2's cancel. So I just have root 2 for X. Then for Y, being R sine theta, that's going to be negative 2 times the sine of 135. So negative 2 times, in the second quadrant, sine is positive. With a reference angle of 45, that's also root 2 over 2. So that's going to be a negative root 2. So the rectangular coordinates are root 2 and negative root 2. And if you think about location, if we rotated 135 degrees and went in the opposite direction, we would be down approximately in the fourth quadrant, and this point here too would be in the fourth quadrant. Root 2 to the right and root 2 down. So we're in the same location. Okay, and the last one. Hopefully you want to pause this and try this yourself and then see if you can get the right answer. Okay, X equals, we're just going to plug right in, 3 times the cosine of negative 120. Now that's in the third quadrant with a reference angle of 60. So that's 3 times, it's going to be negative. The cosine of 60 is 1/2. So that's going to be a negative 3/2. And then Y is going to be 3 times the sine of negative 120. Sine is also negative in the third quadrant with a reference angle of 60. That's going to be root 3 over 2, which is negative. And so that's going to be negative 3 root 3 over 2. So the rectangular coordinates would be negative 3/2 and negative 3 root 3 over 2. And again, think about your quadrants. If you were to overlay the XY axis on there, that would be in the third quadrant. And with two negatives, these would both be in the same location. Okay, now we're simply going to go the other way. We want to write a pair of rectangular coordinates, XY, back the other way into our theta. We're going to use the same process that we used to determine magnitude and direction of vectors in chapter 8. This is literally the same process. So if we go and look at this picture down here, and we, for example, think of R as a vector, the magnitude would be R. And how did we find magnitude? Because magnitude could also be length. We said that R was the square root of x squared plus y squared. If this was a vector in component form, and again, you don't have to write that down, I'm just trying to jog your memory from the vector chapter that we did. If that was in component form, finding the magnitude of that vector was taking the square root of x squared plus y squared. Then to find the theta value, we did the tangent. We saw that the tangent of theta was y over x, so the tan inverse of y over x was how we found theta in chapter 8 when we talked about vectors. So I'm going to erase this, and we're going to go back and look at these formulas and see how it is, in fact, exactly the same. We are not talking about vectors. We are talking about the polar coordinate system, but it is almost exactly the same, so we can directly apply it. So first of all, to find the distance r from the point xy to the origin, we're going to use Pythagorean Theorem. So here's the first piece that we should know. R is going to be the square root of x squared plus y squared. And then to find your theta, you're going to use that tangent function. So the theta is going to be the tan inverse of y over x. Now, one thing that we had to remember with vectors, and we have to keep it in mind here as well, is that when you take the tan inverse, you will only get values in the first and fourth quadrants. So if we have a polar coordinate that is in what would be the second or third quadrant, we're going to have to make an adjustment, and we'll see how we can do that. So remember that the inverse tangent function is only defined in quadrants 1 and 4 if the point is in quadrants 2 or 3, which happens now, here's a key, when x is negative. Think about this. When x is negative, you're going this way. And then your y is going to either put you in the second or the third quadrant. So when x is negative, you're going to have to add pi if you're in radians, or 180 to degrees, or 180 if you're in degrees. Okay. So here it is, making it official in the gray box, converting rectangular to polar. So this again is where we're taking x, y, and we're going to r theta. It is easy, but it takes practice because it can get confusing going back and forth between the two. So if you are given x, y, and you want to go to r, you're going to take the square root of x squared plus y squared. And if you want to get theta, you're going to have to take the tan inverse of y over x when x is positive. But when x is negative, you're going to have to either add 180 or pi radians. Okay, so let's take a look. Find two pairs. Now this one, we need two pairs of polar coordinates for each point with the given rectangular coordinates and round to the nearest hundredth if necessary. So when we take a look at this, 1 negative root 3. Think about the quadrant where this is so that we know if our answer in the end is going to make sense. So if I go 1 to the right and down root 3, this is going to be in quadrant 4. So we would not have to make an adjustment with theta because we're going to be able to get an angle in quadrant 4 when we do the tan inverse. So to get my r value, I'm going to take the square root of 1 squared plus negative root 3 squared. And that's going to be the square root of 1 plus 3, which is the square root of 4, and that is 2. So my r value is 2. Now to get theta, that's going to be the tan inverse of y over x, which is negative root 3 over 1. So that's the tan inverse of negative root 3. So the tangent in the fourth quadrant is negative, and that would be a negative 60 degrees. So my r theta is 2 negative 60. However, I need another one. So if I think about 2 negative 60, it could also be 2 and a positive 300. Just to get another point for the same location. Okay, let's look at letter B. So in letter B, I have negative 3, 6. So that's going to be in quadrant 2, which means we're not going to get an angle that will put us in quadrant 2. We're going to have to make that adjustment. So first let's find r. That's going to be the square root of negative 3 squared plus 6 squared, which is 9 plus 36. And that's the square root of 45, which is 3 root 5. So there's my r value. When I look at theta, that's going to be the tan inverse, of 6 over negative 3. That's going to be the tan inverse of negative 2. And for this one, you can absolutely go to your calculator. Make sure that you are in, well, with this one, I would be in degree mode. Let's put this in degree mode so that we can interpret it a little better. And theta is going to be negative 63.4. Now, that's in the fourth quadrant. That's going to drop it down in the fourth quadrant, so that's okay. That's not okay. So we have right now 3 root 5 and negative 63.4 degrees. However, that can't be our solution because that's in the wrong location. So we're going to make our adjustment. Solutions, because we need 2. So we're going to let 3 root 5 stay, but we're going to take negative 63.4 degrees and we're going to add 180 degrees to that. So that's going to be 3 root 5. And when I add 180 degrees, that is going to be, let's see, 116.6 degrees. There we go. And then the other thing that we can do is we can absolutely keep our angle of negative 63.4, but we can make our r negative, negative 3 root 5. So these are our two solutions. Okay, the last example. All right, it says an ultrasonic sensor attached to a robot emits an outward beam that rotates through a full circle. The sensor receives a return signal when the beam intercepts an object, and it calculates the position of the object in terms of its distance r and the angle measure theta relative to the front of the robot. The sensor relays these polar coordinates to the robot, which then converts them to rectangular coordinates so it can be plotted on an internal map. Suppose the robot is facing due east and its sensor detects an object at 295 degrees. Question A says, what are the rectangular coordinates that the robot will need to calculate? So if we have this robot facing due east, how convenient, 295 degrees is going to be somewhere out here. Well, all we need to do is calculate the rectangular coordinates for that. So we know that x is equal to r cos theta and y is equal to r sine theta. And so we're going to plug those values in and see what we get. So we have 5 times the cosine of 295 degrees. And when we go to our calculator and plug that in, we get 2.11. And then y equals 5 times the sine of 295 degrees. And as I calculate that, I get negative 4.53. And then the value of my rectangular coordinates would be 2.11 and negative 4.53. Okay, question B says, if a previous detected object has rectangular coordinates of 3, 7, what are the distance, which would be r, and angle measure theta of the object relative to the front of the robot? So now we're going to take 3, 7, our x, y coordinates, 3, 7, and turn them into r theta. So to get r, that's going to be the square root of 3 squared plus 7 squared, which is 9 plus 49. That's the square root of 58, which is about 7.62. So there's my r value. And this is a first quadrant angle, so theta should be just fine when we get it. So theta is going to be the tan inverse of 7 over 3. And when I calculate that, theta is 66.8 degrees. So let me write this a little bit better. So 7.62 and 66.8 degrees. So kind of an interesting problem, but again, all they're wanting us to do is convert back and forth. Okay, and that takes us up through 9.3.